All right, so today I want to take a look at section 3.5, which is the start of looking at homogeneous equations. Non-homogeneous second-order differential equations. Still linear, still constant coefficients. So they look like this, where this is not necessarily a zero over here. There's some other function. Okay? Now, it's going to turn out that our work solving homogeneous equations is going to help us in solving these non-homogeneous ones as follows. So here we go. Theorem. Given this, now notice this isn't even constant coefficients. This is sort of your general second order linear differential equation. The theorem is that if you have two solutions, so if y1 and y2 are solutions to this equation, then the difference between y1 and y2 is actually a solution to this equation, which is the homogeneous version of that one. So the left-hand side of the two equations are the same, but the right-hand side has some non-zero function or it has some zero function. Okay. So if you've got two solutions to the non-homogeneous equation, then you can subtract them and you have a solution to the homogeneous equation. To prove that, what we do is we say, well, if I want to show that y1 minus y2 is a solution to this equation, I'm going to plug it into the left-hand side and see if I can get it to equal 0 to show that, yes, it does satisfy this equation, so it is a solution. So if I'm going to plug y1 minus y2 into this, I'm going to need to know what the derivative of it is and the second derivative of it is. So here we go. The derivative of y1 minus y2 is, the derivative is a linear operator, so it's the derivative of y1 minus the derivative of y2. And likewise, the second derivative works that way. I apologize for the humming in the background. I have my 3D printer on pause, and it doesn't like to be quiet. I don't know how much you can hear the humming or not, but anyway, sorry, a little distraction there. So now plug these in. There's y1, plug them into the left-hand side here. So there's y1 minus y2 times g. There's the derivative times p, and there's the second derivative. So you replace them by what they're equal to. Do a little distributing here, multiplying the p of t and the g of t through. Recombined all the stuff here that's got y1s in it. So there's the second derivative, the first derivative, and y1, and then getting the y2s together. And notice that the y2s all have a minus sign in front of them, and so you factor that out. You got this thing. And so this right here is the left-hand side of the equation, but with y1 plugged in. And y1, recall, I'm going to slide back up here, y1 is a solution to the non-homogeneous equation. So the output, if you have this left-hand side, then it's equal to q of t. So that left-hand side for y1 is equal to q of t. Likewise, y2 is a solution to that non-homogeneous equation as well. So you plug y2 into the left-hand side, you get q of t out again, and you get q of t minus q of t is 0. So what happened? We plugged y1 minus y2 into the left-hand side, and we didn't get q of t out, we got 0 out. So y1 minus y2 is indeed a solution to the homogeneous equation, this one. Okay. So the non-homogeneous equation and the homogeneous equation solutions are very closely related, right? If you got two solutions of the non-homogeneous, you can subtract them to get a solution to the homogeneous equation. So that being said, we're going to use that to describe all the solutions of the non-homogeneous. We can already do solutions to homogeneous, so now we want to do the ones for the non-homogeneous. So here we go. Here's the theorem. The general solution of this non-homogeneous equation looks like, every solution y looks like some y sub p, that's going to be a particular solution, plus this stuff, where yp is any particular solution to this equation, and y1 and y2 are a fundamental set of solutions for the homogeneous equation. Right? Remember, the fundamental set is two independent solutions, which we can use to describe all of the solutions for that homogeneous. Those of you who've had linear algebra, you should recognize this theorem from something we did there, that solutions to non-homogeneous systems, that is the general solution of a non-homogeneous system, can be described as a particular solution to the non-homogeneous system, plus the general solution to the homogeneous system, right? Essentially saying, hey, y1 and y2 form a basis for a plane through the origin. They form a basis for, either you think of it as the solution to the homogeneous system, or what we're doing now, the solution space of the homogeneous equation. And what we're going to do is we're going to take all those solutions and just pick them up and move them by some y sub p. That is, any solution, so I got this one drawn over here, is some linear combination of y1 and y2, So if you take that one and just add y sub p onto it, it's like picking the origin up and putting it at y sub p. So this point gets picked up, translated, that whole vector is parallel up here, and you get this solution up here. So everything in this plane up here that doesn't pass through the origin is going to be a solution to the non-homogeneous equation, where everything down here that does pass through parallel plane is solution to the homogeneous equation. Okay. To prove that, we do the following. Okay. Well, let me just point out, what we're going to try to do is we're going to show that everything that looks like this, some particular solution plus something from the homogeneous solution, anything that looks like that is a solution to that. And also anything that's a solution to that equation there can be written in this way. So there's two things we got to do. So here we go. If I have, let's say, y0 and yp are solutions to star, what's star? What did I do? Oh, because I'm going to refer to these equations a lot of times. I made the non-homogeneous equation, I'll call that the 8-pointed star here. And since this is a snow day, we'll call this homogeneous equation snowflake. Okay, so I've got star and snowflake. So here we go. So if you've got two solutions to the non-homogeneous equation by the previous theorem, then the difference of them is actually a solution to the homogeneous equation. Right? So now notice that I can write y0 as yp plus y0 minus yp. This is not rocket science here. This is just basic algebra, that if you take y0 and you add yp to it and you subtract yp from it, then you get y0 back again. Okay. And now from the previous theorem we have that this difference is actually a solution to the homogeneous equation. So I'm going to write this, the stuff in parentheses, as a linear combination of y1 and y2, which were my, what do they call them, fundamental set of solutions for the homogeneous equation. Right? So what have I done? I've said, hey, I've got some solution to the non-homogeneous equation, and I've written it as the sum of some other y sub p plus something from the homogeneous system, from the homogeneous equation for some C1 and C2. Okay. Now going the other way, if I've got something that looks like this, some particular solution of the non-homogeneous equation plus something from the general solution of the homogeneous equation, is that a solution to the non-homogeneous equation? And so I'm going to find out. I'm going to take the derivative, take the second derivative, plug them into the left-hand side, right? So plug them into this left-hand side. There we go. We've got them plugged in, and then we kind of multiply and recombine. So everything that's got a y sub p in it, so there's the second derivative, there's a p of t times the first derivative, there's a q of t times the function, those all come together here. Then everything that's got a y1, so there's a y1 double prime times c1, and there's a y1 prime times c1 times p of t, and here's a y1 times c1 times q. So I've factored out the c1 times all that, and I've got this stuff, and then likewise for the y2s over there. The great thing about this all is that y1 and y2 are solutions to the homogeneous equation, so when you plug them into the left-hand side, you get zeros out, this 0 and that 0. But y sub p is a solution to the non-homogeneous equation, and so you get a g of t out. These were solutions to homogeneous, zeros, non-homogeneous, g of t. And so when you add that g of t plus 0, you get g of t. So plugging in this stuff into the left-hand side, it gave us g of t, which is precisely what it means to be a solution to the non-homogeneous equation. Okay, so that's the general theory. I'm going to go on to do an example now, but I think I'm going to do this in a separate video.